Good morning, Business 270 online students. This is Professor Hassey speaking to you live and in color from Claremont, California, this Saturday morning, August 27th at the appropriate 9:30 hour of the morning. This is our second video of the first week of our study. Each week we will have two videos at the beginning of the week and at the end of the week to highlight the material and review the material of the week's activities. Please make sure you have checked in and reviewed our syllabus and our Blackboard site. A couple of us still have not visited that, and it's Saturday. If you do not go to our Blackboard site for our class by tomorrow, I'll be sending you a little email asking you what's up. So make sure you check in this weekend. You have an assignment due in the discussion post due Sunday at midnight, and we'll take a look at that in just a minute. So let's take a look quickly at what we need to do this first week of our study. Again, this is our Blackboard site for our course. It's designated into a variety of different file folders on the left-hand side, looking at the screen. Course announcements, Zoom and YouTube video links. That's where I post all our videos of our class, of my lectures. Again, the course syllabus and schedule and information file folder, the student discussion file folder. Let's just open that up right now. This is where you post your work for this week. Again, you post your work to this week to week number 1. I would like a 2 to 3 paragraph introduction of yourself and your initial impression of what statistics is for our class. This posting this week is for a grade, about 5% of your grade, course grade, and it's also to show me your ability to access Blackboard and do an assignment. So please make sure you do that by Sunday evening. Then we have the library guide section and each section for our week's work. This is week 1. So this week we have a video lecture, which I have earlier this week, some information about our reading, some PowerPoints of every chapter, and then some review problems. And then remember, the review problems are not for a grade. They're just strictly review of key points of the chapters that you should be familiar with. I also have, for some of you who have yet to have a textbook, I have a PDF of all those review problems in those chapters. And I also have a PDF of all the solutions of those problems in the chapters. So please take a look at that. Again, you do not have to. It's just purely for review and up to date. And we're going to be talking about that a little bit this morning. But first, before we get going, I'd like to show you a brief 10-minute video, again, introducing statistics this very first week.
Welcome to the playlist on statistics, something I've been meaning to do for some time. So anyway, I just want to get right into the meat of it, and I'll try to do as many examples as possible and hopefully give you the feel for what statistics is all about. And really just to kind of start off, in case you're not familiar with it, although I think a lot of people have an intuitive feel for what statistics is about. Statistics. It essentially, well, actually, maybe I should, well, in very general terms, it's kind of getting your head around data. And it can broadly be classified, well, there may be 3 categories. You know, you have descriptive. So say you have a lot of data and you wanted to tell someone about it without giving them all of the data. Maybe you can kind of find indicative numbers that somehow represent all of that data without having to go over all of the data. So that would be descriptive statistics. There's also predictive. Well, I'll kind of group them together. There's inferential statistics. Inferential. And this is when you use data to essentially make conclusions about things. So let's say you've sampled some data from a population, and we'll talk a lot about samples versus populations, but I think you have just a basic sense of what that is, right? If I survey 3 people who are going to vote for president, I clearly haven't surveyed the entire population. I've surveyed a sample. But what inferential statistics are all about are, if we can do some math on the samples, maybe we can make inferences or conclusions about the population as a whole. Well, anyway, that's just the big picture of what statistics is all about. So let's just get into the meat of it, and we'll start with the descriptive. The descriptive. So the first thing that I don't know, that I would want to do, or that I think most people would want to do when they are given a whole set of numbers and they're told to describe it, is like, well, maybe I can come up with some number that is most indicative of all of the numbers in that set. So, or some number that represents kind of the central tendency. This is a word you'll see a lot in statistics books. The central tendency of a set of numbers. Central tendency. Tendency. And this is also called the average. And I'll be a little bit more exact here than I normally am with the word average. When I talk about it in this context, it just means that the average is a number that somehow is giving us a sense of the central tendency, or maybe a number that is most representative of a set. And I know that sounds all very abstract, but let's do a couple of examples. So there's a bunch of ways that you can actually measure the central tendency or the average of a set of numbers. And you've probably seen these before. They are the mean. And actually, there's types of means, but we'll stick with the arithmetic mean. Arithmetic mean. Later, when we talk about stock returns and things, we'll do geometric means, and maybe we'll cover the harmonic mean one day. There's the mean, the median, and the mode. And in statistics speak, these all can kind of be representative of a data set's or a population central tendency or a sample central tendency. And they all are collectively, they can all be forms of an average. And I think when we see examples, it'll make a little bit more sense. In everyday speak, when people talk about an average, and I think you've already computed averages in your life, they're usually talking about the arithmetic mean. So normally when someone says, let's take the average of these numbers, and they expect you to do something, they want you to figure out the arithmetic mean. They don't want you to figure out the median or the mode. But before we go any further, let's figure out what these things are. So let me make up a set of numbers. Let's say I have the number 1. Let's say I have another 1. Let's say I have a 2, a 3. Let's say I have, a 4. I don't know, that's good enough. We just want a simple example. So, the mean, or the arithmetic mean, is probably what you're most familiar with and when people talk about average. And that's essentially you add up all the numbers and you divide by the numbers that there are. So in this case, it would be 1 plus 1 plus 2 plus 3 plus 4. And you're going to divide by 1, 2, 3, 4, 5 numbers. And this is what? 1 plus 1 is 2. 2 plus 2 is 4. 4 plus 3 is 7. 7 plus 4 is 11. So this is equal to 11 over 5. That's what? That's 2 1/5. So that's equal to 2.2. And so someone could say, hey, that is a pretty good representative number of this set. That's the number that all of these numbers you can kind of say are closest to, or 2.2 represents the central tendency of this set. And in common speak, that would be the average. But if we're being a little bit more particular, this is the arithmetic mean of this set of numbers, and you see it kind of represents them. If I didn't want to give you the list of 5 numbers, I could say, well, I have a set of 5 numbers, and their mean is 2.2, and it kind of tells you a little bit of at least where the numbers are, right? We'll talk a little bit more about how do you know how far the numbers are from that mean in probably the next video. So that's one measure. Another measure, instead of averaging it in this way, you can average it by putting the numbers in order, which I actually already did. So let's just write them down in order again. 1, 1, 2, 3, 4. And you just take the middle number. So let's see. There's 1, 2, 3, 4, 5 numbers. So the middle number is going to be right here, right? The middle number is 2. There's 2 numbers greater than 2, and there's 2 numbers less than 2. And this is called the median. So it's actually very little computation. You just have to essentially sort the numbers, and then you find whatever number where you have an equal number greater than or less than that number. So the median of this set is 2. And you see, that's actually fairly close to the mean. And there's no right answer. One of these isn't a better answer for the average. They're just different ways of measuring the average. So here it's the median. And I know what you might be thinking. Well, that was easy enough when we had 5 numbers. But what if we had 6 numbers? What if it was like this? What if this was our set of numbers? 1, 1, 2, 3. Let's add another 4 there. So now there's no middle number, right? 2 is not the middle number because there's 2 less than it and 3 larger than it. And then 3 is not the middle number because there's there's 2 larger and 3 smaller than it. So there's no middle number. So when you have a set with even numbers and someone tells you to figure out the median, what you do is you take the middle 2 numbers. You take the middle 2 numbers, and then you take the arithmetic mean of those 2 numbers. So in this case, of this set, the median would be 2.5. Fair enough. But let's put this aside because I want to compare the median and the means and the modes for the same set of numbers. But that's a good thing to know because sometimes it can be a little confusing. And just, there's nothing, these are all definitions. These are all kind of mathematical tools for getting our heads around numbers. There's nothing, it's not like one day someone saw one of these formulas on like the face of the sun and says, oh, that's part of the universe, that this is how the average should be calculated. These are human constructs to kind of just get our heads around large sets of data. I mean, this isn't a large set of data, but instead of 5 numbers, if we had 5 million numbers, you could imagine that you don't like thinking about every number individually. Anyway, before I talk more about that, let me tell you what the mode is. And the mode, to some degree, it's the one that I think most people probably forget or never learn. And when they see it on an exam, it confuses them because they're like, oh, that sounds very advanced. But in some ways, it is the easiest of all of the measures of central tendency or of average. The mode is essentially what number is most common in a set. So in this example, there's 2 1s, and then there's 1 of everything else, right? So the mode here is 1. So mode, you kind of say, is the most common number. And then you could kind of say, well, hey, Sal, what if this was our set? 1, 1, 2, 3, 4, 4. Here I have 2 1s and I have 2 4s. And this is where the mode gets a little bit tricky because either of these would have been a decent answer for the mode. You could have actually said the mode of this is 1 or the mode of this is 4, and it gets a little bit ambiguous, and you probably want a little clarity from the person asking you. Most times on a test, when they ask you, there's not going to be this ambiguity. There will be a most common number in the set. So now you're saying, well, why wasn't just one of these good enough? Why we learned averages? Why don't we just use averages, or why don't we use arithmetic mean all the time? What's median and mode good for? Well, I'll try to do one example of that and see if it rings true with you. And then you could think a little bit more. Let's say I had this set of numbers. 3, 3, 3, 3, 3, and, I don't know, and 100. So what's the arithmetic mean here? What's the mean here? So I have 1, 2, 3, 4, 5 3s and 100. So it would be 115 divided by 6, right? Right, because I have 1, 2, 3, 4, 5, 6 numbers. 115 is just the sum of all of these. So that's equal to, how many times does 6 go into 115? 6, 115. See, 6 goes into it 1 time. 1 times 6 is 6. 55 goes into it 9 times. 9 times 6 is 54. So it's equal to 19 and 1/6. Fair enough. I just added all the numbers and divided by how many there are. But my question is this really representative of this set? I mean, I have a ton of 3s, and then I have 100 all of a sudden, and we're saying that the central tendency is 19 and 1/6. And I mean, 19 and 1/6 doesn't really seem indicative of this set. I mean, maybe it does, depending on your application, but it just seems a little bit off, right? I mean, my intuition would be that the central tendency is something closer to 3, because there's a lot of 3s here. So what would the median tell us? The median. We already put these numbers in order. Right? If I had given you out of order, you'd want to put in this order. And you say, what's the middle number? Let's see. The middle 2 numbers, since I have an even number, are 3 and 3. So if I take the average of 3 and 3, or if not, I should be particular with my language. If I take the arithmetic mean of 3 and 3, well, I get 3. And this is maybe a better measurement of the central tendency, or of the average of this set of numbers, right? Essentially what it does is, by taking the median, I wasn't so much affected by this really large number that's very different than the others. In statistics, they call that an outlier. A number that, if you talked about average home prices, maybe every house in the city is $100,000, and then there's one house that costs $1 trillion. And then if someone told you the average house price was, I don't know, $1 million, you might have a very wrong perception of that city. But the median house price would be $100,000, and you'd get a better sense of what the houses in that city are like. So similarly, this median, maybe it gives you a better sense of what the numbers in this set are like, right? Because the arithmetic mean was skewed by this they'd call an outlier. And being able to tell what an outlier is kind of one of those things that a statistician will say, well, I know it when I see it. There isn't really a formal definition for it, but it tends to be a number that really kind of sticks out, and sometimes it's due to a measurement error or whatever. And then finally, the mode. What is the most common number in the set? Well, there's 5 threes, and there's 100. So the most common number is, once again, it's a 3. So in this case, when you had this outlier, the mean and the mode tend to be, maybe they're a little bit better about giving you an indication of what these numbers represent. Maybe this was just a measurement error, but I don't know. We don't actually know what these represent. If these are house prices, then I would argue that these are probably more indicative measures of what the houses in an area cost. But if this is something else, if this is scores on a test, maybe there is one kid in the class, 1 out of 6 kids, who did really, really well, and everyone else didn't study, and this is more indicative of kind of how students at that level do on average. Anyway, I'm done talking about all of this. And I encourage you to play with a lot of numbers and deal with the concepts yourself. In the next video, we'll explore more descriptive statistics. And instead of talking about the central tendency, we'll talk about how spread apart things are away from the central tendency. See you in the next video. Let's review a little bit of everything we learned so far, and hopefully it'll make everything fit together a little bit better. And then we'll do a bunch of calculations with real numbers, and I think it'll really hit the point home. So first of all, if we're dealing with let me actually write down, let me make some columns. So if we're dealing with, let's see, we could call it the concept, and then we'll call it the, whether we're dealing with a population, or a sample. So the first statistical concept we came up with was the notion of the mean, or the central tendency, and we learned that was one way to measure the average or central tendency of a data set. The other ways were the median and the mode, but the mean tends to show up a lot more, especially when we start talking about variances, and we'll do in this video the standard deviation. But the mean of a population, we learned, we used the Greek letter mu, is equal to the sum of each of the data points in the population. That's an I. Let me make sure it looks like an I. So you're going to sum up each of those data points. You're going to start with the first one, and you're going to go to the nth one. We're assuming that there are n data points in the population, and then you divide by the total number that you have. And this is this is like the average that you're used to taking before you learned any of the statistic stuff. You add up all the data points and you divide by the number there are. The sample is the same thing. We just use a slightly different terminology. The mean of a sample, and I'll do it in a different color. Just write it as x with a line on top, and that's equal to the sum of all the data points in the sample. So each of the xi in the sample. But we're assuming the sample is something less than a population. So you start with the first one still. And then you go to the lowercase n, where we assume that lowercase n is less than the big N. If this was the same thing, then we're actually taking the average, or we're taking the mean of the entire population. And then you divide by the number of data points you added, you get to n. Then we said, okay, how far, this gives us the central tendency, it's one measure of the central tendency, but what if we wanted to know how good of an indicator this is for the population or for the sample, or on average, how far are the data points from this mean? And that's where we came up with the concept of variance, and I'll arbitrarily switch colors again. Variance. And in a population, the variable, or the notation for variance, is the sigma squared. This means variance. And that is equal to, you take each of the data points, you find the difference between that and the mean that you calculate up there, you square it, so you get the squared difference, and then you essentially take the average of all of these. You take the average of all of these squared distances. So you take the sum from I is equal to 1 to n, and you divide it by n. That's the variance. And then the variance of a sample mean, and this was a little bit more interesting, and we talked a little bit about it in the last video. You actually want to provide you want to estimate the variance of the population when you're taking the variance of a sample. And in order to provide an unbiased estimate, you do something very similar to here, but you end up dividing by n minus 1. So let me write that down. So the variance of a population, the variance of a sample, or sample variance, or unbiased sample variance, and that's why we're going to divide by n minus 1. That's denoted by s squared. And what you do is you take the difference between each of the data points in the sample minus the sample mean. We assume that we don't know the population mean. Maybe we did. If we knew the population mean, we actually wouldn't have to do the unbiased thing that we're going to do here in the denominator. But when you have a sample, the only way to kind of figure out the population mean is to estimate it with the sample mean. So we assume that we only have the sample mean. And you're going to square those, and then you're going to sum them up. Sum them up from I is equal to 1 to I is equal to n, because you have n data points. And if you want an unbiased estimator, you divide by n minus 1. And we talked a little bit before why you want this to be an n minus 1 instead of an n. And actually, in a couple of videos, I'll actually prove this to you. One, I'll prove it maybe experimentally using Excel, and then which wouldn't be a proof, but it'll just give you a little bit of intuition. And then I'll actually prove it a little bit more formally later on. But you don't have to worry about it right now. Now, the next thing we'll learn is something that you've probably heard a lot of, especially sometimes in class. Teachers talk about the standard deviation of a test, or it's actually probably one of the most used words in statistics. I think a lot of people, unfortunately, maybe use it, or maybe use it without fully appreciating everything that it involves. But the goal is, well, we'll eventually, hopefully, appreciate all that it involves soon. But the standard deviation. And once you know variance, it's actually quite straightforward. It's the square root of the variance. So the standard deviation of a population is written as sigma, which is equal to the square root of the variance. And now I think you understand why a variance is written as sigma squared. And that is equal to just the square root of all that. It's equal to the square root, I'll probably run out of space, of all of that. So, the sum, I won't write the top and the bottom, that makes it messy, of xi minus mu squared, everything over n. And then if you wanted the standard deviation of a sample, and it actually gets a little bit interesting, because the standard deviation of a sample, which is equal to the square root of the variance of a sample, it actually turns out that this is not an unbiased estimator for this. And I don't want to get too technical for it right now. That this is actually a very good estimate of this. The expected value of this is going to be this, and I'll go into more depth on expected values in the future. But it turns out that this is not quite the same expected value as this. But you don't have to worry about it for now. So why even talk about the standard deviation? Well, one, the units work out a little better. If let's say all of our data points were measured in meters, right? If we were taking a bunch of measurements of length, then the units of the variance would be meters squared, right? Because we're taking, meters minus meters. This would be a meter. Then you're squaring. You're getting meters squared. And that's kind of a strange concept if you say, the average dispersion from the center is in meters squared. So first, when you take the square root of it, you get something that's, again, in meters. So you're kind of saying, oh, well, the standard deviation is x or y meters. And then we'll learn a little bit if you can actually model your data as a bell curve, or if you assume that your data has a distribution of a bell curve, then this tells you some interesting things about where all of the probability of finding someone within one or two standard deviations of the mean. But anyway, I don't want to go too technical right now. Let's just calculate a bunch. Let's calculate. Let's say if I had numbers 1, 2, 3, 8, and 7. And let's say that this is a population. So what would its mean be? So I have 1 plus 2 plus 3. So this 3 plus 3 is 6. 6 plus 8 is 14. 14 plus 7 is 21. So the mean of this population, you sum up all the data points, you get 21 divided by the total number of data points, 1, 2, 3, 4, 5. 21 divided by 5, which is equal to what? 4.2. 4.2, fair enough. Now we want to figure out the variance. And we're assuming that this is the entire population. So the variance of this population is going to be equal to the sum of the square differences of each of these numbers from 4.2. I'm going to have to get my calculator out. So it's going to be 1 minus 4.2 squared plus 2 minus 4.2 squared plus 3 minus 4.2 squared plus 8 minus 4.2 squared plus 7 minus 4.2 squared. And it's going to be all of that, and that looks a little bit funny, divided by the number of data points we have, divided by 5. So let me take the calculator out. All right. Here we go. Actually, maybe I should have used the graphing calculator that I have. Let me see if I can get this thing. If I could get this. Oh. There you go. Yeah, I think the graphing one will be better because I can see everything that I'm writing. Okay, so let me clear this. So I want to take 1 minus 4.2 squared plus, let me write it down, plus 2 minus 4.2 squared plus 3 minus 4.2 squared plus 8 minus 4.2 squared. Right, I'm just taking the sum of the squared distances from the mean squared. One more, plus 7 minus 4.2 squared. So that's the sum. The sum is 38.8, so the numerator, so this is going to be equal to 38.8 divided by 5. So this is the sum of the square distances, right? Each of these, just so you can relate to the formula, each of that is xi minus the mean squared. And so if we take the sum of all of them, right, this numerator is the sum of each of the xi minus the mean squared from I equals 1 to n, and that ended up to be 38.8. And I just calculated it like that. I just took each of the data points minus the mean squared, add them all up, and I got 38.8. And then I want to divide it by n, which is 5. So this n up here is actually also 5. Right? And so 38.8 divided by 5 is 7.76. 7.76. So the variance, let me scroll down a little bit. The variance is equal to 7.76. Now, if this was a sample of a larger distribution, if this was a sample, if the 1, 2, 3, 8, and 7 weren't the population, if it was a sample from a larger population, instead of dividing by 5, we would have divided by 4, and we would have gotten the variance as 38.8, 38.8 divided by n minus 1, which is divided by 4. So then we would have gotten the variance we would have gotten the sample variance at 9.7 if you divided by n minus 1 instead of n. But anyway, don't worry about that right now. That's just a change of n. But once you have the variance, very easy to figure out the standard deviation. You just take the square root of it. The square root of 7.76, 2.78. 2.7, well, let's say 2.79 is the standard deviation. So this gives us some measure of, on average, how far the numbers are away from the mean, which was 4.2. And it gives it in kind of the units of the original measurement. Anyway, I'm all out of time. I'll see you in the next video. Well, actually, let's figure out, we said if this was a sample, if those numbers were a sample and not the population, then we figured out that the sample variance was 9.7, and so then the sample standard deviation is just going to be the square root of that, the square root of 9.7, which would be 3.1. Anyway, hopefully that makes it a little bit more concrete. We've been dealing with these sigma notation variables and all of that so far, so when you actually do it with numbers, you see it's hopefully not that difficult. Anyway, see you in the next video.
Okay, there's a couple of videos. The first one was pretty simple, pretty easy. It's the very first part of our course. And then I threw in the second video, which is not to freak you out, but that's where we're heading to in the second week. That's where we're leading to. Samples, standard deviation, analysis of data. And that's where we're heading to into the week 2. But up until then, we're practicing some problems. We're looking at the material, but that's give you an overall view of what the first part of this course is all about. Now, next week, you're going to be getting next week on Monday, a case study to do. And that case study will be reviewing the definitions talked about in these first 4 chapters. What is statistics? Describing data in tables and graphs, describing data in numerical measures, describing data in displaying data. Those are the first 4 chapters of our class. And that's really what was the first video we saw today. Now, that case study is just a series of problems, examples from those 4 chapters, which I'm going to have you do and put together. The thing I wanted to tell you, though, is you have a series of problems. Here they are right here that are posted in your Blackboard from each one of those chapters. There's chapter 1, there's chapter 2, here's chapter 3, here's chapter 4. So these problems go over the definitions of these various problems, and this is what I would like you to review and correlate that to your reading. Again, if you don't want to do this, that is fine. This will be your template and your guide next week when I give you the case study. You'll see a question asking you about what is the level of measurement of something. Please explain that. Well, if you can refer to these exercises and these review problems as a way of getting the answers. Now, what are the answers? Here are the answers also supplied in your textbook in week number 1. Here are the answers to those questions, chapter 1, chapter 2, chapter 3, and chapter 4. So again, you can use these as your guide in studying the material. You can refer to the textbook, but again, if you don't want to do this review, you might want to review maybe 1 or 2 problems from each chapter. But then when you have your case study next week, and this will be for a grade, is when I'll ask you questions in these review problems are your template or sample of those types of case study questions. So that's the purpose of this, and we'll do this same procedure week after week throughout our course. In some respects, the course gets a little bit easier to figure out because when we start doing our case papers in a couple of weeks, those are just written papers explaining data that I give you. This case study and the midterm will be actual problems from our review problems of these initial chapters in the text. And these 2 videos tonight will make up the midterm examination in a couple weeks. Those 2 videos highlight the work of that midterm. So now you have it all laid out in front of you. Your job is to review the material. Again, remember, let me go back to this and show you. In your each individual weekly file folder, this is week 1, is a description of each one of these key points of each chapter and a PowerPoint that explain those key points that you can review. That plus the videos I post, that plus the review problems will get you in pretty good shape to get prepared for the graded work. But again, this week's problems is not graded work. It just sets the stage of learning definitions, beginning our course, and acts as a template for future problems that you will be given grades on in our course. But don't forget, you do have 1 grade this week, which is your student introduction. And please post that by Sunday evening. So that gives us our basis for our very first week. Your priorities this week have been to, number 1, read the course syllabus, get familiar with Blackboard, understand the key points and definitions of chapters 1 through 4, and then do your discussion folder, posting something to Blackboard, which gives me a little bit idea about yourself and what you think statistics is. Our next video will be on Monday, August 29th. We'll talk about week 2, following up more on this information of week 1, plus talking a little bit about chapter 5. So have a great weekend, everybody. You got to keep up to date with these videos and this information. If you fall a little bit behind, then we're going to have some problems. So try to stay up to date with the material. If you have any questions, you can post to the discussion forum. You can send me an email. And remember, we have student hours every Thursday night. So thanks, everybody. Have, again, a great weekend, and we'll see you next week.